Well, welcome back everyone so far. Any questions at all to start us out while we're waiting? Okay, got about 30 seconds and we'll get going. Well, it's official, folks. Welcome back. For today's class, well, you kind of know what we're doing. We're finishing off the notes section 7.4. Then we're going to walk into pretty much what's a review section for us, strategy for integration. Our author does have a lot of reading in there that does give some pretty decent strategies, but we're just going to mainly practice problems that are out of context, meaning when we were in section 7.1, we just knew every problem is basically integration by parts. When we were section 7.2, we knew we needed a trig sub, or that 7.3, and so on and so forth. But when you take all these problems and just mix them together, take out the context, that's when you're really learning those methods. You have to decide what made it an integration by parts problem, or what made it be partial fraction decomposition. So we're going to treat this as really just a big review kind of section where we highlight how we pick the methods on a problem by problem basis. I didn't ask too many problems on this one, so it's a pretty short set. And I think the notes indicates that we'll probably finish this on Monday, which is a good idea because I realized I made a mistake when we were talking about this section last class. I mentioned very typical problems on exams for partial fraction decomposition are cases 1, 2, and 3. Only because case 4 is a really pretty interesting process. It could take a lot of algebra to solve the coefficients. I thought I had a case 4 on this one, but it turns out I don't. But I want to add one. I'm going to revise these notes when we come back on Monday. I'm going to add a new additional problem that really is case 4 because we deserve to see why it's not on the exam. But there is still a partial fraction decomposition problem on there that is challenging, like a case 4 problem. It's just not strictly case 4. But aside from that, just as a reminder, the Moodle website is going to change quite a bit over the weekend on this week right here. That's when the definite coverage and review materials are going to start getting posted. And most importantly, to inform your studying, I'll be posting, first of all, the formula sheet included as the last page on the exam 1. So again, you'll know what to have next to you when you're studying, what things you're expected to have memorized.
Hey, so.
Sorry, go ahead, Carter.
Oh, I'm so sorry. I was yelling at my dogs. I did not know my mic was on. I'm so sorry.
I have 5 dogs, so I totally understand. No worries. Other questions at the moment? Okay. And just to go along with that, I have 5 dogs. One of them is a red heeler, and that one has to take fluoxetine. So if you ever get a red heeler, just be aware that squirrels drive them insane. And they're a great dog to get you outside. But aside from that, let's get back into section 7.4. I think fluoxetine is the generic and very nice way to say, what is it? I forget. Prozac, thank you. Yeah. So back to the actual content of the day. Here we're just going through the partial fraction decomposition problem. We looked at several various cases, but one thing I want to remind folks, when you do this as a problem on homework, you definitely want to show out all the steps on solving for the coefficients, only because we are expected to do that in an exam setting when it comes up. But don't worry about taking advantage of extra tools. Check your work. It's sometimes kind of heartbreaking to do all that work and have the coefficients wrong. This syntax right here in Wolfram Alpha, that web address, is a great way to check your work after you've done it by hand to see if you're on the right track right before integrating. And that could save you a lot of time, because if you make one coefficient be off, the thing you're integrating could suddenly become extremely complex when it was never intended to be. So this is almost like survival sometimes when you're learning this the first time. But for this down here, let's give this a try. we have distinct factors, but that factor is suspicious, right? If it was an x squared minus 1, we would be happy because x squared minus 1 is reducible. We can factor it as x plus 1, x minus 1, but x squared plus 1 causes major difficulties because we're not using complex numbers, square roots of -1. Other thing you could look at on this one is test it with a discriminant or solve an equation set equal to 0. Either of those things are going to reveal you can't factor it. In other words, it's irreducible. Let's go the discriminant route since that's our author's preferred method and it's a pretty good idea to always come back to. B squared minus 4ac is going to be, well, there is no b coefficient, so that's 0 squared minus 4 times the a coefficient, which is a 1, times the c coefficient, which is also 1, which then equals -4 altogether. Because it's less than 0, it means if you set this equal to 0, you're going to have a square root of -4 in the quadratic formula, complex solutions. And so this is what tells us irreducible. Because the power on here is 1, that means we are in case 3, a non-repeated but irreducible factor. So that informs how we should start this out. We're going to take this whole thing, x squared minus 2x minus 1, divide by x minus 1, x squared plus 1, and decompose it according to the partial fraction decomposition theorem, case 3. But the first portion is nothing too special. That's degree 1. So we just say a over x minus 1. But that's the irreducible factor right here. When we go to put in the irreducible, x squared plus 1, anyone recall what we should be throwing up into the numerator this time? Good call, folks. It's going to be not constant. It'll be linear. So we need 2 coefficients to handle it. bx plus c, as you all said. So that's what makes this a case 3 problem, that right there. And notice when you go to use the partial fraction decomposition theorem, there is a pretty interesting pattern. Unless something is repeated, for non-repeateds like this one, where we just write x minus 1 down once, numerator is degree 0, denominator is degree 1. So the denominator is higher by 1. Same over here, denominator is degree 2. So numerator is degree 1. The denominator wins by 1 degree as well. Again, this is only if they're not repeated. So this is what we're trying to solve. We'll take the next step of clearing the denominator, which means I'm taking this whole thing, multiplying it over here. I've also multiplied on the left-hand side, so it's cleared off. We are left with x squared minus 2x minus 1 equals, when you put that whole thing right over here, the x minus 1 portion has canceled, and we obtain a times x squared plus 1. Then we do it again over here. Take that whole thing and multiply it against bx plus c, just visualizing it with parentheses now. This time, x squared plus 1 cancels this off, leaving behind just the x minus 1. So that's our important step, clearing out the denominator. We have a new equation for which we can solve a, b, and c pretty rapidly. That looks like a c right there. Let me fix that parenthesis. So that's the first stage of this, getting down to this equation. Any questions at all on the clearing denominators portion? Okay, beyond that, we do the fun part of pick a good value for x that's going to allow us to solve for a coefficient. We don't want to pick a value that's going to give us 3 unknowns, in other words, because then you need 2 additional equations to solve the 3 unknowns, and you're essentially in a linear algebra situation. So we're trying to pick a value for x that's going to kill off most of these, but not all of the values a, b, and c, leaving just 1. Any volunteers for a good choice to start? 1's a great choice, absolutely, because if you pick 1 from right here, it's destroyed coefficients b and c, but it leaves coefficient a. So let's say set x to 1. On the left-hand side, we get 1 minus 2 minus 1, so just a negative 2. 1 squared plus 1 is just 2 times a, plus all of this is now 0 due to that term going to 0. So we've got one coefficient already. A has to be equal to negative 1. Well, now we need another one. Any questions so far? I think 0 is a good choice because 0 will get rid of the b coefficient, and that means we can start solving for our c coefficient. A still survives, but we know the value of a, so we're in good shape. So 0 is a good one, but you also might have noticed there is a bit of a struggle whenever you're doing a case 3 and case 4 gets much, much worse. There is no good value to pick right here for a. So if this factor was repeated, our work, the complexity of it, has grown a tremendous amount. You would really potentially have to solve a system of 3 linear equations and 3 unknowns to do it effectively. There is an alternate route, so that's a problem I didn't include in 7.5, but I'll add it to the end of that document as an edit. But first, if we pick 0, here we just get a negative 1 equals, coefficient a still survives, this is just 1 times a, plus, over here it's 0 plus c, times negative 1 when we dump 0 in that location. This is not too bad of an equation to solve because it really involves just one unknown. We'll substitute in the value for a and say negative 1 goes here, and then minus c for the rest. Looking at that really carefully, this would immediately imply c has to be 0. If you have the same number here and here, and whether it's an opposite positive sign or a million times c, c is 0, or just add negative 1 to both sides. 0 equals negative c also implies, if you divide by negative 1, c coefficient has to go to 0. That's nice in a way. That means we don't have to deal with this one at all. That goes to 0, so it's effectively just canceled. That'd be my reminder for the next step. If we can get the coefficient b, we're all set. So one last number to pick. Good choice. I think 2 would be a good one to go on this one. You could pick negative 1, but now you're navigating multiple negative signs. I think this is a more stable way to go. Any number would work. You just don't want to be too hard on yourself, so don't pick 2,000. You get the same answer, but there's no reason to write that much. So the strategy is, just like in real life, find the way to do the least amount of work possible so you're as accurate as possible. Plugging 2 here gives us 4 minus 1, so that looks like a negative 9. Let me know if my arithmetic goes sideways. That's a weak spot for our night class for sure. 2 here is going to give us a 5a. Here we're going to get plus 2b plus c times 1. Yeah, go ahead. Negative 1 right here. Oh, so if I plugged in 2, I had positive 4 minus 4. Good call for a positive 1 there. Thanks for spotting that one. That was some shoddy arithmetic. But again, arithmetic's the first thing to go when you get tired. So it's good to be a little bit more careful when you do these kinds of things as you go. So let's see what else we have going on here. Thanks again for the fix on that one. We have an a coefficient. We have a c coefficient. So we'll substitute the values into this equation. It's now negative 1 equals 5 times negative 1. So just a minus 5 there. I was trying to select that as blue. Plus, we can just simply drop these parentheses now. 2b plus 0. So this is a fast equation. We now have negative 1 is negative 5 plus 2b. Add 5 to both sides for 4 equals 2b. It's kind of relaxing to be in a calculus class solving these kinds of linear equations. But it's also a danger because you're tempted to go fast and make mistakes. So even though it's not so complicated, still it deserves us to be methodical and careful. Divide by 2, and b equals 2. So my claim is that's how it decomposes. A negative 1 here, a 2 here times x, and no further coefficient. Any questions at all, folks, on finalizing this decomposition? Okay, so we have a way to rewrite this part right here. This integration is very tough. Try to find an antiderivative of something that looks like that. I would have no hope of attacking it unless we saw it through this lens. This is the antiderivative of, in place of a, just drop in the -1 from our work above below, divide by x minus 1, then plus 2x, divide that one by x squared plus 1, dx. So this is where we'll finalize our answer. And it's not too bad to start. This is a nice integration problem. This one's less nice, so we'll give a little bit more time on that one. It's a U substitution right here by the red dot. And if you haven't determined just by visual inspection what it could be, this is a good one that I would personally do, just showing the steps out. But if you felt like you've done this one a lot and you know the punchline behind it, and you sideline the U substitution, that would be okay on your homework. But just make sure you're ready to do that same thing on an exam setting so that you're not drawing a blank. Sometimes the best thing to do is just do the U substitution on your homework so you're really well practiced and prepared on the exams, just as a safety net. But here's the next step. Antiderivative of this is just -1 multiplying the natural logarithm of x minus 1. And then on this one, I'll take an extra step and go plus. Here I'm just splitting up the integral. Integrate 2x over x squared plus 1 dx. It's not so bad. We just would probably start with u equals the entire denominator, x squared plus 1 could go in. Then du is 2x dx, the differential. And ordinarily we divide out the 2, but you always want to look before you leap because this time we don't need to. This 2x dx is all of that right there. And this portion is just going to go right there for a u. So this is negative natural log absolute value x minus 1. Through this substitution, we're going plus integrate 1 over u du, where my color coding is just these pencil tools here, drawing these out. So that's a fast antiderivative. We get negative natural log absolute value x minus 1 plus natural logarithm absolute value of u plus a constant. Kind of annoying because we keep on doing additional steps when it's a u substitution. So, sometimes what people do on this is just take that whole thing to the margin and solve it there, then plug the answer back in on the next step. That way you're not carrying down all these things that are never changing line by line. If it's not too annoying to you, then no harm done. But if this is a lot of stuff on the left, separating out that one integral becomes a pretty good strategy for organization and keeps your hand from getting too tired. So it's negative natural log absolute value x minus 1 plus natural logarithm. We undo our substitution, but that's a positive quantity, so we can simplify the absolute values by just dropping it, x squared plus 1, then plus c. So this is a non-negative quantity. It's non-zero, as small as it ever gets is a positive 1. That means we did it, folks. The antiderivative of all of this stuff right here, after you split it apart, is just this. Any questions at all in finding that value? Well, we did it, folks. Congratulations. This is the partial fraction decomposition theorem. I hope that you feel like after you do the homework on this that it's tedious because of this, but it's at least straightforward, whereas trigonometric substitution, that's pretty technical step by step by step. It feels a lot different. Really, the major thing you want to really get going on whenever you're doing problems in this section is it's all about seeing what the patterns look like in this example 2 right here. So it's a good one to come back to. Come back to it in the blank lecture notes in 7.4. Think of these as just basically worksheets now. You could go back to here and see if you can redo it again and just double check what we have on Moodle as the solutions. So that alone is a great way to study this. And once you see how all these patterns come down, the rest of the steps is just following your nose through the algebra and then finally integrating once you get to these steps here. Okay, well, we did it, folks. Let's save up these notes and go over to the next section then. Any last final questions then before we skip to 7.5? Well, not that we're skipping anything. Move over to 7.5. Yeah, absolute value on this one was, yeah, just do the x squared. And another thing to mention though is this is just something that I do as a stylistic choice. If you left absolute values in, no harm done. Some people says you should simplify a little bit further, but truly not a big deal. You have the right quantity either way you look at it. Other questions at the moment? Okay, let's let this save up. Takes a bit of a moment when it gets kind of a longer document. And here's our next section. Again, congratulations. This is the main content that we just finished on the last set of notes for exam one. Exam one is all about integration. I know it can be kind of dry because we did like no applications whatsoever this whole semester, but we're saving most of it for chapter 8. Chapter 8 is all about those applications. Think of what all we're doing in chapter 7 is getting the tools needed as we proceed to those next applications down the line. So 7.5 as a review section starts off with a gigantic table. We've used this one already dozens of times in this class, if not over 100 times, it feels like. This one is the one that's the exception to watch out for, but it's really just a good one-stop shop for looking up weird esoteric derivatives like, say, that one or that one. Great table for that kind of stuff. I'll be including some of these anti-derivatives on the actual exam 1 through exam 2 and the final, just because I'm not expecting you to memorize certain things like these. Sometimes with the integrals, we literally just look them up. You're not meant to be a glossary of every single antiderivative on the planet. So starting off on this one, these are mixed integrals. So our major objective is to pick a method. Any volunteers for what method could work on this one? Absolutely. This one looks like a good u substitution method because there's a square root function. Inside, we have 1 plus a logarithm function squared. So lots of function compositions indicate probably you want to use a u substitution. So let's mention that here. We'll use u substitution. And as far as u substitution goes, there are several strategies. You can be like a really fine razor and just take the smallest function possible, natural log x. Or you can use like a blunt hammer and take something even bigger, 1 plus natural log x squared, or even bigger, root 1 plus natural log x squared. Usually you don't want to go too big because it's going to fail at some point. I think this as a u substitution, the entire denominator, probably not a good way to go. If I was going to do this myself, I personally would just take natural log x as my u. But for the folks that like to go big, let's do this time. Root 1 plus natural log x squared. We're going to take that entire thing there and just see if it works out. I think it does. I hope it does. We'll see what happens. I practice it. Let's see if it works out again on the second try. The only downside of doing big is your differential is more complicated. So let's work this out carefully. It's a good review on just differentiation, which we haven't done a lot so far. Du is going to be the derivative of this square root function. Right away, I would use a shortcut for dealing with square roots. We mentioned this before, but let's say it again. Root x prime, so the derivative of root x, is as a big punchline, just 1 over 2 root x. Fantastic shortcut because square roots come up a lot in calculus. They're used for distances, so any application, you're probably differentiating square roots often. Well, if the application has distances. So first thing we do when we differentiate, we go to the outermost function. How do we spot it? Imagine you had a number 5, and your calculator is about to do this. First thing it does is the natural log of 5, then it squares it, then it adds 1, Then finally, after all that, your calculator takes the square root. The last thing you do in order of operations is your outermost function. We differentiate that first to get derivative of any root is 1 over, I'm going to leave the 1 off because we're getting more stuff by the chain rule, but it's 1 over twice the root of something. The something we're mentioning is the inner function to the square root, 1 plus natural log x squared. And because that input right here is not just x, we must multiply by its derivative. It would go right here, but if we're multiplying a fraction that way, it really just goes up into the numerator. So that's why I left the numerator blank on this one. Derivative of what's inside is the derivative of the constant 1, so it's 0, plus this derivative. But that's just a whole new chain rule. We have to differentiate the power 2 function first. That one goes like this. That's just the good old power rule. We left off this power 1, that's completely fine as well, but just for emphasis, that's what happens. Then we throw a function on the inside, natural log x. And because this is a chain rule, we chain on the next derivative, the derivative of that inner function. But that derivative is just a times 1 over x. Actually, I have a change of heart. This looks a little distracting because it feels like a prime. So I'm going to delete that power just so it does not as a big of a distraction. So last thing to make it a differential is go dx. Let's take another look at this whole mess. The 2's cancel. So that's good news there. Other thing that happens is you can re-express times 1 over x like this. The x would just go into the denominator algebraically. So this is du equals natural log x still there. 1 over x by the red dot just gives you x down below like that. That's multiplying root 1 plus natural log x squared dx. But all of this, every single bit of it, is the entire integrand this time. Sometimes that actually just works out, and it's a slick method when it does. Because if you went u is natural log x, you need 2 u substitutions. You have to put them together, which means you have to undo both substitutions. This one turns out just by kind of a miracle with how this was arranged to be the fastest way to do this one, potentially. There's possibly other things you could try. But if that happens, if you've taken out the whole thing for du, you're integrating 1. And that's not so bad. The antiderivative of 1 is back to u, add the constant, and u is just this whole thing right here. So this becomes root 1 plus natural log x. Let me fix the penmanship on that. Squared plus a constant. So this integral here, which looked really complicated, it's really just this antiderivative. And through that shortcut, it kind of makes sense. If you differentiate that, this whole portion goes to the denominator. Then you start multiplying these things through chain rules. And that's where the x down here, natural log x, comes in. It's almost as if you're doing the same problem over here, finding the differential of this u. In fact, it literally is the same process. So sometimes integrals are really weird. This kind of almost feels circular, but that's the true antiderivative. Any last questions, folks, on surviving this one? Okay, let's make this up to the class because it is kind of a review section in the first place. Should we try it out in kind of the normal way where you picked u equals natural log x, or should we go to the next one? Any volunteers for a direction? It's always weird to choose your own adventure, right? Because anyone who speaks out has become the leader of the class on that question there.
Could we go over it?
Absolutely. Thanks for mentioning that. I think that was either Catherine or Haley. I'm not too sure, but thanks for mentioning that. Be very
Yeah,
happy
of course.
to. Okay, so let's call this method 2. I'm glad someone says let's give it another try because honestly, if this was a real exam problem, that would be like a Hail Mary, right? I think most people probably would not have started with that. So we're going to try it out in a different way. Method 2. Let me start with grabbing the whole integral. And now we have the method 2 approach. Again, like I mentioned, if you want to go as fine as possible in picking your u, I think a lot of people would try natural log x. We went wide and took the whole square root, and maybe something could work as a compromise. Maybe 1 plus natural log x squared really does work. Let's try the opposite end. We're going from really big as a u to really, really small, just natural log x. We'll compare the methods and see which one we prefer. Honestly, I personally prefer method 2 only because it's a more natural way to go at it. Next, du becomes 1 over x dx. The 1 over x dx would be this. Because x is in the denominator, it is literally a 1 over x in your problem. It's combined with the dx. And this part right here, well, that's part of the u substitution as well. So going out this route, we have integrate u above, just following the color coding pretty much, x dx, both reconvene as a du on the right. Then we have a root, 1 plus u squared. Now that we've used method 2, we started with u substitution. You could pick another method. You could try trigonometric substitution, but I don't know if that would be wise on this one. Not because it doesn't work, but because if you're power 1 here and power 2 down there, it suggests just another u substitution is a natural choice. I would use maybe trigonometric integration, u equals tangent theta perhaps, if this was something like maybe u power 3. The next u substitution is going to be tricky if we can come up with it at all. Sometimes it's supremely tricky. But in this configuration, strategy is try a u substitution again. You could call it u again, but we would have a conflict of notation, right? You could fix that by writing down maybe a u hat, changing the symbol. Could go a subscript, u1. I would strongly discourage that as a symbol because prime is just a huge distraction to calculus. Or just make it a w. There's nothing special whatsoever about u whatsoever. You could go w, y, maybe not x because that's a conflict of notation again. I'll go with a w. So it's a w substitution, but same as before. However, my question for the class is, what should w be this time? 1 plus u squared? I'd say that's a good call because the differential naturally involves that u right above. So 1 plus u squared for w. That means dw, that's the differential, giving us a dw on the left. We get the derivative of this part, which is just a 2u. And then go du, because u is the variable of differentiation here. We do have the u du, but we could lose the 1/2 if we'd like by just putting it right over here. 1/2 dw is u du. So now this u du right here just turns into that. And w is just going to go into that location. Running out of colors to color code it, so let me use this right here, just to convey that that's going in as a w. So this is now, let's do the yellow portion first because a 1/2 can emerge right in front of the integral sign in that way. We have 1 over root w, and the du right here turned into the 1/2 dw. So the 1/2 has just been scooted outside of the integral over here for a little bit more simplicity in dealing with that. So that's a nice integral right here. We just want to put this in the right format to use the power rule. So next good steps is, this is 1/2 w to the power of negative 1/2. 1/2 because that's the real exponent when we indicate a square root, and negative because the base got moved up to the numerator. So now we are ready for an antiderivative. It's 1/2. New power on W is just adding 1. So that's adding 2/2 for a 1/2. Divide by that new exponent, 2/1. Add a constant. And now all we have to do is undo all of our substitutions. It's not too bad, but we have layers to get through, so let's get through them. First, we can call this just a square root. The coefficients in front cancel, and W was 1 plus U squared. So following that color coding, we get to that stage. And then next, the U itself was natural log X, so we drop that in. It becomes root 1 plus natural log X squared plus a constant. At that stage, we got it, folks. It feels like it might have took longer, but the differential here was technical enough that even though it's compact, this might have been the longer way to go, really, because you have to be so careful with it. But no matter how you do it, even if you picked a different U substitution than any of these two, others could still work on this. Everybody ends at the same thing, root 1 plus natural log X squared, only differing by a constant. Well, any last questions, folks, on this extra look at U substitution? Carter says, how did we do that last step? By that last step, are you referring to, say, this line right here, where we undid the last thing? Or are you referring to maybe here to here?
I just don't see how we went from the W to the power of 1/2 down. I don't see that.
Oh, gotcha. So the one thing that happened was the power 1/2 right here, we can think of as W 1/2 being the square root of W there. Then the next thing that happens was from this W here, we plug it into that location, and that's where we are getting that 1 plus U squared in that position. Then another layer of substitutions is whatever we said U was gets dropped in over there, but our U is the natural log X, so that's how our U transformed to the natural log X there. Does that make sense on visualizing how we went from that W all the way over to there?
Yeah, that makes a lot of sense. Thank you.
Yeah, absolutely. I'll leave this arrow diagram down here because sometimes that's just what your eyes need to really see it. Yeah, go ahead.
Why is it a 2/1 in front of the W to the 1/2 power? Wouldn't it just be 1.5?
I gotcha. So the trick with this one right here is, let's take a look at it as sort of a problem just sort of on its own. If we took, say, the antiderivative of power, maybe it's, say, 3. Way better problem, right? So this is kind of cheating, but it's a good analogy. If we were integrating W cubed, we would go W power 4. So the power has to always increase. But then we divide by whatever that exponent happened to be. So we would go 1/4 and then finalize with a constant. So then what happened with this one, if we have something a little bit worse, well, okay, a lot worse, really. If we're integrating W power negative 1/2 dW, following the same process here as an analogy, we would go W to the power, add 1 to this, which is adding 2/2. So it'd be a 1/2. Then we would divide by 1/2. But if you go, say, 1/1/2, all it does is it implies just one additional step. Although, at least doing it this way, it's matching up the analogy directly, right? We're following the same exact procedure either way. But the final thing that happens on this one is dividing by a half means you're just multiplying by the reciprocal. So that's where it turns into W power 1/2. So we're just taking the reciprocal of here to get to there. Does that make sense for that one? Awesome. And that's usually kind of my pattern of attack. If I get a fractional exponent after integrating, I always go here to here and take the reciprocal. Not because it's required, that's only because it saves one tiny step of simplifying the complex fraction here to an ordinary value. Other questions at the moment? Absolutely. Let's give that a try. I'm kind of curious on that because I don't think I've ever done the trig sub on it. Or hang on, we're thinking of this part right here. Let's give that a try. That could be kind of interesting. So if we decided, because this is kind of the danger in calculus, if you study the trigonometric substitution section very, very hard, really exquisite study session, imagine. Now it's really deep in your head and everything looks like a trig sub problem. That's kind of dangerous in its own way, because how would this go as a trig sub? Who knows? We're about to find out. That's a good question. Let's start with u equals, what would you say that the substitution should be? Sine, tangent, or secant? It is a tangent, good call. Reason this one ought to be a tangent is we have the identity 1 plus secant squared theta equals tangent squared theta. This is the core identity that makes our substitution work. And this left-hand side feels a lot like that right there. So we'll pick u equals tangent theta. Now we're on our way on that. We can take du. It's secant squared theta d theta. So that's what's going to replace this portion right here. Next is the root. 1 plus u squared becomes root. Oh, yeah, it is. Dang, that's a weird identity it threw down there. Thanks for spotting that. I should have said tangent squared theta equals plus 1 equals secant squared theta. Maybe the identity I was trying to think about is that tangent squared theta then is going to become secant squared theta minus 1. I don't think that's really relevant to us. We want this identity here. So let's keep it as that identity. Thanks for spotting that weird trigonometric non-identity. That's the real one. So using this real one, plugging in u into this location, we get 1 plus tangent squared theta in this location now, following the color coding, which I forgot. Now through the right identity, this turns into a secant squared theta. And upon taking the root, we get just a secant theta. So now we know what happens to this location right here. Putting it all together, here's our brand new integral. Antiderivative of u. So tangent theta up above. Divide by the root 1 plus u squared. That's a secant theta. Then from this portion right here, du, I'll go times to say I'm throwing in a differential. The right-hand side, secant squared theta, d theta. And here's what we've got. Integrate, upon simplifying, tangent theta, secant theta. Hey, this one turned out kind of nice in a way. I was a little bit worried we'd use a new substitution to get through this one, but it's actually clearing up kind of nice. Anyone spot this antiderivative? Yep, this one's just a secant. Derivative of secant is secant theta, tangent theta. Doesn't matter if the order is wrong. Multiplication's commutative. So secant theta plus a constant is what we will get handling this here through the trig substitution. But this isn't over yet, right? We would have to undo that substitution. So we would go from here, right? Tangent theta is u over 1. If we like the SOHCAHTOA, here it is. If you're not a fan of it, I'd say don't worry about it. A mnemonic is only useful if it actually helps to memorize stuff. But what it's trying to say is tangent equals the opposite side divided by the adjacent side, which just makes it a little bit more streamlined when we build out this triangle here. We're going to say u is opposite theta, put over here. 1 is adjacent to theta, here. Pythagorean theorem on this diagram would say take 1 squared plus u squared, square root it. 1 squared just looks weird. I almost don't want to leave it that way. That is part of our integrand, so that tells us we are probably on the right track. It would be super rare to make two mistakes or mistakes that cancel out, where this conveyed down to here in our diagram, but we are still doing it wrong. Okay, so now we need a secant theta. Secant theta through the SOHCAHTOA is not adjacent divided by hypotenuse because we're dealing with a reciprocal. We go hypotenuse, root 1 plus u squared, divide by the adjacent, which is a 1, so we can leave it off here if we prefer. Add a constant. Then, oh, hang on, what did I do here? Yeah, 1 plus u squared. And then from there on, we would have to come back way up here, say u is natural log x. So this turns into root 1 plus natural log x squared plus a constant. So although this is not recommended, this is a great review on trigonometric substitution all on its own, but it's also a good thing that we did this problem because it's also kind of a warning, right? Just because you can use trigonometric substitution does not mean you should. If you find a simpler method, say this, well, hang on. Yeah, this method, another u substitution, we called it w, strong encouragement to just try it out that way. Even though it looks like it took a lot of steps, these steps are much more technical in my opinion. So you have to be careful or going this route. Well, any questions at all, folks? Seeing that problem, that's kind of cool, 3 different ways. Just as a reminder, you never have to do this in class. Pick one way if it works, even if it looks ugly like this right here, it's a great answer if you've got the right antiderivative. So no extra points for finding the fastest answer, unfortunately. Well, our goal here is to practice more problems like this. So if you have any other interesting problems to try out, don't hesitate to throw them out there. Like this one here was a great one to review. But for the next one, let's try out this thing. T sine t cosine t, all multiplied. That's terrible because you can't find the antiderivative of t, antiderivative of sine, and cosine and just put them together. It never goes as easy as that when it's integrating. So anyone spot what we should try on this one? It is by parts, good call. Let's go integration. By parts. As far as integration by parts go, you'll notice we usually do integration by parts when there are 2 factors. That's because we did the product rule of 2 factors when we derived it. Nothing is going to stop you from deriving the integration by parts method with 3 factors, except that gets really complicated, and we would have to derive it to even see how it goes. So what we're really going to do to start this one off is a trigonometric identity. This is just not very helpful if we want to get through the problem rapidly. So we'll use the double. Let me try again. The double angle identity, of which there are many, but you might have noticed in the notes that for some strange reason, one identity has come up quite a lot in this class, and it is this one, the double angle identity for sine. Twice sine theta cosine theta becomes sine twice the angle. So if we apply that here, feels like it doesn't work, right? Because we just have a sine t, cosine t. We're missing the 2, but huge, wonderful technique in anything algebra and calculus is multiplication by 1 can do a lot of magical things for you. That 1 can turn into a 2 over 2, sine t cosine t. You could split this up as 1/2 times 2 sine t cosine t, and the double angle identity happens right here. This turns into 1/2 sine 2t. So doing this extra work right here means we don't have an overly complicated integration by parts. We'll just use the standard one with 2 factors. So our problem is now 1/2 antiderivative of t sine 2t. Let me fix that parenthesis, dt. So yes, we're still using integration by parts, but we had to do this little side adventure by the double angle identity. Well, worth it because this problem is now much easier to get through. And just because this is a review section, let's put down our acronym, LIATE, is our method for picking U. Once U is picked, you have your DV settled. And going down the line, the big red flag on this one is there is an algebraic portion, T. That's the A part. The T part is the trigonometric function. It says if you put the trig function here, it's probably going to be a complicated process. We should just put the algebraic function T right here instead. That leaves behind sine 2t, dt, and now we're on our way. Let's complete the table. Du is dt, and this is a tricky one because of the 2 right in front of sine. Anyone spot what the v variable should turn into down here? Exactly. So the -1/2 would come in. That 2 that you spotted came from that part right there. Good call. Then the rest is, as you said, cosine 2t. So that's what we'd be working on with this one. And again, all you're doing with v is you're integrating the dv portion. And it's not a bad check each time you do this. If you have v set down here, imagine differentiating it. -1/2 cosine 2t prime would become, we carefully differentiate this, a -1/2 is a constant carrying in, derivative of cosine is a negative sine, 2t. Chain rule right here says multiply by the derivative of 2t, which is a 2. And if you clean up this as much as possible, yeah, that's just a sine 2t you're looking at. So doing a little check like that, even if you're just doing it in your back of your mind's eye, your mental chalkboard, that's a good thing to pause on. Look at it real carefully, make sure it's all in line, and then we're ready to go on the next part. Any questions so far, folks, to this stage? Okay, here's our next part. We have to be extremely careful with that factor of 1/2. It's came up a couple times in section 7.1, but it's easy to miss. That 1/2 has to distribute through our total answer minus the plus c part. Then from over here, because we're using integration by parts, it's not a bad idea to always write this in. It becomes muscle memory, so when you do this in an exam problem, even if this is all you wrote, that's worth partial credit as well. Don't know why I erased that. But writing this down is just a way for your mind to see what everything is going to be plugged into, what order, and so on. So we have 1/2. Looking toward the table on the right, I'm just going to read out these values on the left. So in place of u, throw in a t. In place of v, throw in the -1/2 cosine 2t. Copy the negative sign, the integral sign, and now we're still at v. So copy in -1/2 cosine 2t again. The last part is du, from which we put in dt. So if we can do this last integral, and that looks very obtainable, the whole problem is done. So here's our next steps. 1/2 times the quantity, -1/2 t cosine 2t. Here we should pull out all constants. -1/2 is multiplied by -1 for +1/2, leaving integral cosine 2t dt. Then from here out, we just about have it. For me, I'm making a choice, just a stylistic choice of just leaving that 1/2 factored out on the outside. All up to you what you'd like to decide to do. You can distribute it in, leave it out, factor more stuff out. But at the end of the day, as long as it's algebraically accurate and you've combined all your like terms, the simple cancellations, I'm not too picky on how you format your end answer. So let's copy in -1/2 t. Let me fix my penmanship on there. Cosine 2t. I think my penmanship goes sideways because my hand just gets tired towards the end of class. Then from here, we have a plus 1/2. But instead of copying that down, let's give the full answer for this part in one shot, which is really not too different from what we did when we went from dv down to v. The only thing extra is you have to account for the 1/2 that's already here. Any volunteers to say what this whole thing would convey down as? Exactly, good call. It's over 4 because each time we take an antiderivative and it's a 2t, we're dividing by a new 1/2 factor. And we check that through just applying the chain rule. So over here, another antiderivative means you're multiplying this by a 1/2, it's a 4th. Good call, it's positive because the antiderivative is a sine 2t, whose derivative becomes a positive cosine. Here I would close the brackets, add the constant, and this finalizes the problem finally. Kind of a long one on this one. Here's just a quick border to separate our helpful computations on the right and our formal answer on the left. Well, any questions at all, folks, on running through this one? Okay, well, that's just another antiderivative down. This one's pretty nasty because, again, I don't know how I would even start this unless I use the double angle identity. I almost never try to do integration by parts with 3 factors. It's usually discouraged. Try to find a way to get out of that. If you ever have to, you've got to come up with that formula. It's not nice to work with. Much like there's a quadratic formula, but there's also a cubic formula, just becomes extremely complicated out of nowhere. But let's come down here and try out the next problem of the day. Okay, like a lot of these problems that we're looking at here, this is the one that's going to require some heavy duty methods, but it's just a case 2, not the case 4. We'll come back and add another part E, case 4, when we revise these notes. But on this one, there are 2 good competing methods that can work. We just have to pick a method, so I'll leave it up to the class. What feels like a good way to go here? Unfortunately, yes, this could be a trig substitution. You could also make it a U substitution, but those are very tricky to do sometimes. And this is one of those times where if you knew exactly how to run through the U substitution, you can make it work in a fast way. But the trig substitution might actually be faster because it's just so direct. U substitution here requires ingenuity to get going. So let's start by saying x is, if it's a 1 plus x squared, that's another tangent theta. Tangent thetas came up a couple times. Let me know if you want a different one of these notes, and I'll be happy to include it after we add a new problem like this one. But if we go x is tangent theta, then, like we did on our prior problem looking at this, we'll say dx is secant squared theta, d theta. Next, we just simplify the root right over here. Root 1 plus x squared. If you came over here and you just said very boldly secant theta, I would say that's just fine. It would be an alert to me that you've done this at least a dozen times. You're seeing what the pattern should be. So small shortcuts like that, that's just an indication to me that you've done this a lot. But I would encourage you only do that if you really have done that a lot. If you feel like you still need to practice this more, definitely write it out because it'll help you on the exam when you have to do these steps. You don't want to think what was the shortcut if you forgot the shortcut in an exam setting. This is a much more rememberable way to go. So in place of x, we are putting in tangent squared theta. Then we use that good old trigonometric identity. Let me try it again. 1 plus tangent squared theta becomes secant squared theta. So this is root 1 plus secant squared theta. Or excuse me, this is root secant squared theta. Let me try again on that. Gotta love Control Z. Which turns into just a secant theta, like we said. So that's pretty much the punchline for the square root portion. X cubed, all we do is we add power 3 to that. Dx is full on replaced by everything right here. The secant squared theta, d theta. So this is us finalizing the problem. Well, getting there at least. Going top to bottom, left to right, it's tangent cube theta. Divide that result by secant theta for this part. Multiply that whole quantity by secant squared theta d theta. So now in this portion, we're just integrating tangent cube theta, secant theta, d theta. So a lot of work to get down to this stage, but this is the hard integral. This one's actually a lot nicer. This is now in section 7.2. When these come up in section 7.2, we divert over to the U substitution method. We just have to find what is the best function. Should it be tangent or secant? Anyone see which is a good call for this one? Absolutely, good eye on that. If we made it tangent, then the derivative of tangent would have been a secant squared. So that differential is incompatible here. There is no secant squared. So make it a tangent, theta. Note here, even though it's tangent cubed, we always pick tangent power 1 to make this type of U substitution work. So let's recolor code things. We have a tangent theta there, then du, or hang on, we didn't say tangent theta, we said secant theta. Sorry, getting mixed up on my thoughts there. Let me try again. Going with the original good and correct suggestion, that should have been a secant theta. Then the differential du is secant theta, tangent theta, d theta, which means we sacrifice one factor of tangent here, leaving behind tangent squared, but tangent squared is what we want to see because that identity enters into the problem yet again a second time. But in a section 7.2 problem, it's good to really organize your integral. Instead of leaving it a tangent cubed, it's way easier to see how it comes together if you make it a tangent squared. They go tangent squared times secant theta, tangent theta, d theta. So equality is not damaged because tangent by tangent squared gets us back to tangent cubed. And now that whole thing is your du. We just have one small problem right here. So we go and grab tangent squared theta. It's much like doing the square root portion on the first substitution. Tangent squared theta by identity is secant squared theta minus 1. But then our same U substitution enters into the picture, so we have U squared minus 1. So all of this right here is that. Any questions so far, folks, to this stage? Okay, so these are kind of good problems in a way because we were reviewing multiple sections all in one, trying to do this one single problem. So now next step, in place of tangent squared theta, drop in the thing we did on the right, U squared minus 1. And this whole portion to the right of the bullets right here, the multiplication symbol, was just to organize to say it becomes du. And that means as fast as your hand can write, we're getting the antiderivative. This first part is a third u cubed, then minus u at a constant. So ordinary antiderivatives from here on out. Go back to what we said u was and drop it in. This is 1/3 of secant squared here minus secant squared, or excuse me, minus secant. So secant squared theta minus secant theta plus a constant. And now, because we started with a trig substitution and we did multiple substitutions, we have to undo even this down below here.
Isn't that a secant cubed?
Oh, hang on. Yeah, absolutely. Not sure where that power 2 would have came from. Thanks for spotting that one. That one deserves the all-important red on there. So should have been a cubed here and here. I was almost there with the 1/3, but so far is not close enough unless we get that power exactly right. Thanks again for spotting that one.
Okay, it's getting a
Other
little late.
questions? Sorry, say again.
I just said it's getting a little late.
Yeah, it definitely is. Easy to miss those little things there. And speaking of which, we've got 3 minutes to undo the last substitution. I think we can make that happen. Come over here and re-express this as tangent theta is x divided by 1. Let's lose the SOHCAHTOA and just say that that is always opposite over adjacent so that we can build the right triangle. Here's x at the opposite end, 1 at the adjacent end. This feels like deja vu. 1 plus x squared would then go here by Pythagorean's theorem, which is that bit. So now secant theta, again, really feels like deja vu out of nowhere, is 1/3. We do a secant over here. It's going to be the hypotenuse divided by 1. So it'd just be that. But we're also raising it to the 3rd power. So I think a nice way to write this in would be 1 plus x squared to power 3/2. Denominator here, 2, is just because of the square root. Numerator power here came from that power over here. Then go minus root 1 plus x squared coming from that last secant theta right over here. Add our constant c, and we did it. It's a tough problem, really, because multiple substitutions to get through. You know, sometimes when you're doing a trig substitution, you actually almost hope it's a definite integral because those are way faster. You never have to come back to this kind of work, for example. But we did it, folks. This is doing it in a straightforward way. It's a little bit longer, but it does get the job done at least. Any last questions at all, folks, before we call tonight?
Yeah, I do have a question.
Yeah, go ahead.
So, will the test questions be similar to the ones we're doing in class now or ones we find in the book?
I would say that the ones that you're doing in the book, specifically the ones that look like, say, these problems right here, they're meant to be pretty similar to the ones that we're doing in the actual lecture notes. So these problems here. So when I go to write down the exams, I look at each one of these sections on what was actually assigned, each one of these sections on what we actually did. I'm trying to write an exam that's similar to both sets of problems. I'm also controlling them for complexity so the exam isn't too long. The exam questions are potentially just a little bit easier than the ones that you got through right here. A little bit easier than the ones that we got through here as well, just so that it's not like a 3-question exam with 3 awfully long questions. But does that help out with that question there?
Yeah, there's some I struggle with in the book, but then like when we do in class, they feel 100 times easier. So I'm just trying to gauge where I need to be for the test.
Gotcha. I would say that they're going to be pretty similar to these, but maybe just not as long on each one.
Got it. Thank you.
Yep, you betcha. Well, have a great weekend, folks. If you do have questions, feel free to stick around. I'll be happy to help. Otherwise, I'll see you all next Monday. Hey, question over here?
I feel like I did something wrong here because the answer that you have on there has sign, but mine doesn't include sign. So I'm trying to see where it went wrong.
Oh, actually, your answer could be right because, oh, hang on, you did a U as cosine on this one.
Yeah, because I did
Oh,
design
yeah.
the original one, but then you told me to swap it because it's the higher degree.
Yeah, I suddenly just remembered that conversation. So let me double check the work here. Differential looks good. So you'd have a negative, and then from here, it would be the du. Then for sine power 4, it's just 1 minus u squared, u power 9. Then that looks great for the distribution. And double checking the limit change, that's pretty tricky too. Pi over 2 goes into cosine and it's 0. 1, yeah, that looks great. If you wanted to, you could swap the limits of integration, and then they would just delete the negative sign, but it's not going to harm it to leave it just like this. So now
I didn't know
U9
that you could do that. That's pretty
to 11, yeah, it's kind of a cool process. It basically looks like this. Antiderivative from a to b, f of x dx, is negative antiderivative from b to a, swapping the limits, fx dx. And usually the only reason you want to do that is because it just looks weird, right?
Oh,
From
so
a larger
from
number
zero,
to a smaller. So it's no harm to leave it as is.
So that way I don't have to distribute that negative like I did, but. Oh, well.
Yeah. So when the
I have a
negative
question,
distributes in,
but-
that looks good. So this is then 12 and then 14. Then we will come over here and get a cosine on this. Power 10, power 12, power 14. Evaluate from 0 to 1. And no, I think you're on the right track with this one.
Okay.
All you needed to do is plug in the values of 0 here, here, and here. Change it around and plug in the values of 1. But just to double check, let me see how I did as well.
Your answer that you have the cosine and the sine, and I was like, this is gonna come.
Well, this one I just came out with a 1/210 for this one.
Oh, I'm thinking of, I think I was looking at the, initial equation.
Oh, I gotcha.
Right here.
Gotcha.
Oh,
Darn it.
okay.
No worries.
That would
But
be
yeah,
fun.
you're on the right track with that. Just evaluations left over. And it should come out to,
1/210.
actually, if I could look at your work just one more time. One small thing is, because it's a definite integral and you also change your limits of integration, you actually don't have to put in cosine back in. If you did, you'd have to put in 0 to pi over 2 again. But if your limits of integration are changed, this is how we usually do it in class. You really just want to plug 0 into that, that, and that. Plug 1 into that, that, and that, and you're on your way.
Okay.
That makes sense for that one?
Yeah.
Awesome.
Thank you.
Yep, absolutely.
For 29, I got a different answer.
Is this 7.2 as well?
Yeah. So
Gotcha.
And I plugged it in like on Wolfram Alpha and
Yeah.
it got the answer that I got, so I was kind of.
Oh, that's kind of curious. You
I
know,
do have the paper over there, so you can see what I did for 29.
oh, gotcha. Let's take a look. And
I just did the exact same thing I did for 25, and the only thing that was different was the like order of magnitude and the denominators.
yeah, so this was,
So on the side.
gotcha. So 29.
Yep.
The thing that's kind of crazy about this one is that substitution absolutely works,
Mhm.
but so does that one, secant x. So this is one of those problems where there's two correct
So there's
options.
two.
Yeah, the only reason I picked secant x on this one is because it was the highest power.
Mhm.
That meant I turned this into a tangent squared that became that.
Oh, I see. Yeah, you have the one that I got.
Yeah.
Okay.
On yours, you know, it works out just as well. You just have higher
Yeah,
complexity here.
29.
Yeah, but it comes out to exactly the same thing.
Yeah.
I mean, it does not look at like it, but these
Yeah.
are algebraically
I
equivalent.
just saw that I could do the exact same thing I did on the previous ones.
Gotcha.
Okay.
Yeah,
If they're both exact.
there absolutely are. That's something that happens a lot in this section. There's lots of equivalent answers, which makes it confusing to put down an actual answer key. Yep, take care. Yep, have a great weekend.